Now I want to introduce categories and functors, which are a basic language that's used throughout algebraic topology. So what do we mean by these? So a category, curly C, say, consists of, well, firstly, a class we'll call obj.C of mathematical objects. Which could be groups or rings or whatever. Those would be algebraic examples, or topological spaces, metric spaces, other things like that. And then for every pair of objects, we're going to have a set. Okay, this is one other ingredient in the structure of the category. A set CAB, and the elements of this set are going to be called morphisms from A to B. And as a kind of notation, write AFB like that, or F colon A to B. And these just mean that F is an element of this set CAB. Okay. In other words, F is a morphism from A to B. And then the next ingredient so for each object, we're supposed to have a morphism from the object itself. So this is going to be called idx, and this is going to be called the identity morphism. And then the final kind of ingredient is that there's a composition rule and okay, so this is a kind of product structure, a rule which defines for us an element G composed of G ring F in CXZ for each pair consisting of morphism F from X to Y and G from Y to Z. So we've got, this is all the data that we've got, and it's supposed to satisfy two axioms. So axioms are axiom E. We've got some F from X to Y. Then F composed with the identity on X is equal to F, which is the same as id Y composed with F. Okay, so remember, so axiom C provides for us these morphisms, id X and id Y. Axiom D provides for us this rule which defines these compositions, and they're supposed to fit together in this particular way that if we compose an identity on either side, then we just get the original thing. And then final axiom, I've got some, say, W, say, and then E to X, and F to Y, and G to Z. Okay. So then there's two ways we can group these to compose them. We can firstly compose G and F and then compose that with E, or alternatively we could first compose F and E and then compose that with G, and we're supposed to get the same answer. Of course, so this is like the associativity axiom in a group, and again, we also use the word associativity for it. So that's what we mean by a category. And so basic example, so we could have the category of groups. I'll maybe write this on the next screen, but let's just say it for the minute. We have a category of groups, so the objects would just be groups. The morphisms, group homomorphisms in the usual way, functions from A to B that preserve the group operation. And then in the category of groups, the identity morphism is just the identity maps from a group to itself, which is a homomorphism by a trivial argument. And then for ingredient D, we're supposed to have a composition rule, and so if you've got group homomorphisms, X, Y, and Z are groups, and F's a homomorphism from X to Y, and G's a homomorphism from Y to Z, then you can just compose the functions to get a function G composed with F from X to Z, and then it's just like a very simple lemma that the composite of two group homomorphisms is a group homomorphism, so that G composed with F, we can regard it as a set, as a morphism in the category of groups. So we've got a composition rule that behaves in the right way. And then these two axioms, E and F, are kind of completely obvious in that context. So I've got a couple more examples in a minute. So most of our examples have the following shape. Objects are sets with some extra structure. Okay, so like a group structure or a ring structure or a metric or a topology. And morphisms are functions that preserve the relevant structure. And then we've got to say what the identities and the composition rules are. So id x is the identity function. And well, we've not really been very precise about what we mean by a structure or preserving a structure, but basically, in every case, it's just kind of completely obvious that the identity preserves whatever structure you're talking about. Once we've made precise what that means, and composition of morphisms is composition of functions. And then you have to check that the composite of structure preserving maps, structure preserving functions still preserves the structure. Again, that's typically quite easy. Okay, so I kind of said this verbally a minute ago. we've got a category of groups where the objects are groups. Morphisms are group homomorphisms. And there's also similarly a category of rings. Okay, so that's another category. But then we also have some kind of topological examples where we've got category metric as a category of metric spaces. And the morphisms are continuous functions. So morphisms from x to y are just continuous functions from x to y. Okay, and again, so identity functions continuous. The composition of two composable continuous functions is again a continuous function. So that gives us a category. And underlying these, there's an even more basic example. A category of sets where the objects are sets and the morphisms are functions. And there's various subcategories, ways that we can cut down a category to make it smaller. So one example is we can have AB is the category of abelian groups. So you've got the category of all groups, and then contained within that, you've got the subcategory of abelian groups. Just for future reference, when we're talking about abelian groups, we'll normally write the operation additively. Okay, so in an abelian group, the group operation will be called plus, okay, and so the identity element will be called 0. Okay, so that's a category of abelian groups, and then you can also have fin ab is the category of finite abelian groups. Okay, so these are examples where you've got you just cut down the class of objects. You don't instead of all groups, you've only got the abelian ones and or the finite abelian ones. But we've basically got the same kind of morphisms right here. Category AB, the morphisms are just group homomorphisms, and similarly for fin AB. But then we can also do a slightly different thing where we, instead of cutting down the objects, we cut down the morphisms. We could do set ing. The objects are sets. The morphisms are injective functions. Okay, so for this to make sense, we need to check a couple of things. We need to check that identity maps are injective, so that they count as morphisms in set ing. That's kind of obviously true. And then we also need to check that the composite of two injective maps is injective, so that we've got a proper composition rule in this set ing. But that's also easy to check. So that's one thing we could do, or we could do. So we've got the category of sets and injective functions, or we could have the category of groups and surjective homomorphisms. Another kind of interesting one is here in the category of metric spaces, we took the morphisms to be all continuous functions. But we had a little lemma a while ago which says that distance decreasing functions are continuous. Okay, you've got a function f. We said that it's distance decreasing if the distance from fx to fy is less than or equal to the distance from x to y, and that implies it's continuous. And so you could have a subcategory which I call metric 1. Again, the objects are just metric spaces, but in that category, the morphisms are distance decreasing functions. So that's a decent menu of examples of categories and their morphisms.